In this video, I'll be talking about linear Diophantine equation, which is ax plus by equal to c. And as we can see that we are talking about equations, so we are obviously interested in knowing the solution of this equation. So let's consider an example of a linear Diophantine equation before we come to the result of what is a linear Diophantine equation and what are the solutions result. So let's consider an example as 3x plus 6y equal to 18, and we are obviously interested in knowing the integral solution. So you can see that 3 into 4 plus 6 into 1 is 18. This is true. Then I can also have 3 into minus 6 plus 6 into 6. This is also equal to 18. That is also true. We can also have 3 into 10 plus 6 into minus 2. This is equal to 18. So there are many integral solutions. So now to know what sort of integral solution do we have, what is the result based on linear Diophantine equation, we have this theorem as it states linear Diophantine equation. This has a solution if and only if d divides c. So there is a condition on if and only if d divides c, where d is the GCD of a and b. So that is the first result that we want to prove, that whenever d divides c, this linear Diophantine equation ax plus by equal to c has a solution, and if ax plus by equal to c has a solution, then d is a GCD which must divide c. So this must hold. And the second implication, we want to show that if x naught and y naught is any particular solution of this equation, then all the other solutions are given by this expression. So x is equal to x naught plus b by d times t, and y is equal to y naught minus a by d times t, and t is integral. So a and b are picked up from this coefficient of x and y, and we know what is d. D is the GCD of a and b, and what we know as c is the right hand side of this equation. Now let's first prove this implication if and only if, and then we will come to this result for finding all the other solutions of the Diophantine equation. So now in the proof, first I want to go for this implication if and only if, and even in this, let me to assume that ax plus by equal to c, this admits a solution. So if this admits a solution, let us consider the solution as x naught and y naught. So suppose that these are the solutions. So I'm just considering for these integral values. So this means ax naught plus by naught equal to c. So if this admits a solution, what we need to prove that d must divide c. And what is d? So now we already know, and let d is the GCD of a and b. So whenever d is GCD of a and b, so we know d must divide a and d must divide b. And I can also write a is equal to dr, and we can write b is equal to ds. And this one already holds. So just substitute the value of a and b in this case. So we know that c is same as a is dr times x naught plus what is the value for b. So I'm just substituting the value for b from here, and this becomes ds times y naught. Take d common, so this is r times x naught plus s into y naught. This all is an integer, and d is of course also an integer, but from here we can see that c comes as a multiple of d. So this implies d divides c, and that holds our condition that we wish to prove, that d must divide c if this admits a solution. Now conversely, I want to take that given is d divides c, where d is the GCD of a and b. So this is the converse, and we want to prove that ax plus by equal to c, this have a solution. So we want to prove that it has a solution for some x naught and y naught. So now whenever d divides c, so we can say that as d divides c. So from here I can write c as dt for some t belonging to integer, and we also know that d is the GCD of a and b. So this is given to us. So this implies d must be written as a linear combination of a and b. So let's write d as ax plus by for some x and y which belong to integer. Now taking this, so we can take this, take x naught and y naught belonging to integers for which this relation holds. So I am assuming that for some x and y naught for which d equal to ax naught plus by naught, this relation holds. So we have taken the particular values. Now once we know that d is equal to ax naught plus by naught, it holds for the particular values of x naught and y naught. Multiply t by both sides, so this become at x naught plus b times t y naught. And we already know that dt is same as c. So dt is same as c, so just replace this by c. So we get c is equal to a. Now club this t with x naught plus b times t y naught. So this means C is equal to A x dash plus B y dash. And here x dash is t x naught, which belongs to integer of course, and y dash, which is also t times y naught, this also belongs to integer. This means now linear Diophantine equation has a solution for this particular x naught and y naught. So we say linear Diophantine equation admits a solution for x dash, that is equal to t times x naught, and y dash equal to t y naught. Now this x dash and y naught, these are arbitrary, so we can just simply say that C is equal to ax plus by. This admits a solution, and hence that proves our the if and only if condition. It completes the if and only if condition. And now we want to prove the second assertion of the theorem, that if x naught and y naught is any particular solution of this linear Diophantine equation, then x equal to x naught plus b by d times t and y equal to y naught minus a by d times t, t belongs to integer, is the any other alternate solution. And now because x naught and y naught satisfy this linear Diophantine equation, so let me to call this as a x naught plus b y naught. This is equal to C. And let's also call this any other alternate solution because we want to find out the condition on x. So let's take x dash plus y dash, where x dash and y dash, these are any other solution of this linear Diophantine equation. So now from here we can see that this is same as a x dash minus x naught, keep x on one side and keep pi's on the another side. And we notice that D is the GCD of a comma b. So whenever D is the GCD of a comma b, so that means I can write a as d times r and we can write b as d times s, because we have already taken the greatest common divisor out from here. So this means that GCD of r and s is equal to 1. They are relatively prime. So now just substituting this value for a and b as dr and ds, and then we can cancel the d on both sides. So this will leave us a term r times x dash minus x naught equal to s times y naught minus y dash, where the GCD of r and s is equal to 1. Now recall here Euclid's lemma. In my last video I have talked about this. This is a divided by bc, and whenever the GCD of a and b is equal to 1, this implies a must divide c. So now I'm going to apply this lemma onto this. So you can see that we can consider that r divide this quantity. So we can consider that this side is a multiple of r. So whenever r is taken as a multiple of this, so this means I can write r divide s into y naught minus y dash, or we could have also taken that s divides this whole quantity. So in that case I could have written s divides r times x dash minus x naught. So in any way we can progress, and we know that GCD of r and s, this is equal to 1. So this implies r must divide y naught minus y dash, and here this will implies because the GCD of s and r is equal to 1, so that means s must divide x dash minus x naught. From here we can say that y naught minus y dash is equal to r times some t, and here also we can say that x dash minus x naught is s times t, where t belongs to integer. So this implies y dash, this is equal to y naught minus rt, or I can say from here x dash, that is equal to x naught plus s times t. Now we have seen that a is d times r and b is d times s. From here you can calculate the value for r. So r is a by d and the value for s is b by d, and they are integral values. So just substitute this value back into here. So this is y dash equal to y naught minus a by d times t, and here this value becomes x dash, that is x naught plus b by d times t, and t belong to z, which is an arbitrary integer. Since we have found the value for x dash and y dash, these are any other solution that we have selected for the linear Diophantine equation. So now we want to verify that ax dash plus by dash is equal to c. If this hold, then d can be treated as the any other integral solution. So let us do that also. A into x dash is x naught plus b by d times t. So that is the value for x dash, plus b into the value for y dash, y naught minus a by d times t. And let's open this. So this is the left hand side. I have taken it from the above expression. This value is same as ax naught plus by naught. And then the second term is ab by d minus AB by D times T. So that is the second expression, A multiplied by B by D, and here B multiplied by A by D. So this is same as, you can see that AX naught plus BY naught. These two terms get cancelled, so this is 0 into T. So that is same as AX naught plus BY naught. And this is the given solution, that X naught and Y naught is the solution for the linear Diophantine equation. So certainly this is C. And this means that this side is also equal to C, and this is same as we have substituted the value AX dash plus by dash equal to C. So that means this x dash and y dash satisfy the linear Diophantine equation, and these act as the any other solution for the linear Diophantine equation. So we now consider a linear Diophantine equation. The question says solve for x and y belonging to integral value, and the second question says solve for x and y which are positive integers. So now let's see how do we solve this problem. To solve this problem, now look at the steps of the linear Diophantine equation theorem we have just done. We say that if I compare this with the linear Diophantine equation, that is Ax plus By equal to C, and this has a solution if and only if we said that D divides C, where D is the GCD of A and B. That means I need to know what is the D. So let us first find the GCD of A and B. That means here let's first find out the GCD of 172 and 20. So I need to find GCD of 172 and 20. So this is the first thing that I need to know. And to note this, we'll apply the Euclidean algorithm. So applying the Euclidean algorithm, so we can find out the GCD of this, and we know that 172 is of course a bigger number than 20. So let's do that. 8 into 20 plus 12 is the remainder. Apply repeatedly. 20 is 1 into 12 plus 8, and then I can take 12, that is 8 into 1 plus the remainder is 4, and now you can see that 8 is 2 into 4 plus 0. So from here we can see that GCD of 172 and 20, this is 4, and we also see that 4 divide 1000. So this is what is the given as C. So if divide this, that means Ax plus By equal to C, or here it is 172x plus 20y equal to 1000. This admits a solution. So it is possible that it may not have admitted a solution, but so the first condition that we must need to check whether D divides this right hand side or not. So yes, it divides. Now the question is how to find the solution. Now let's see, to find the solution I need to take from this expression what is the linear combination of 172 and 20 in terms of the GCD. So we know whenever GCD of A and B is given as D, so we can write D as Ax plus By for some x and y belonging to integer. So let us find out what is A and B from this extended Euclidean algorithm, and in the extended, that means I need to trace back from the remainder. So the last remainder is the 4. So from here I can write 4 as 12 minus 1 into 8, and look at now the last remainder, that is 8. So this means this is 12 minus 1 into, substitute the value for 8 which is from here, that is 20 minus 1 into 12, and then let's take out the common terms, club these to 12 and this 12, so that is 2 into 12 minus 1 into 20. And now look at what is the next last remainder here, that was 12. So substitute 12 as this expression. So this will give me 2 into 172 minus 8 into 20 minus 1 into 20. That gives me 2 into 172. And then we have minus this 2 multiplied by 8, that is 16. And then we got minus 1 here, so that is minus 17. So this is minus 17 into 20. So we have the expression 2 into 172 plus minus 17 into 20. So if I just look at now from this expression, so we can now say that 4 is equal to 172 into 2 plus 20 into minus 17. But we need an expression of this equal to 1000. So look at here. From the given question, we needed 1000. So to get it right hand side 1000, multiply this equation by 250 on both sides. So we get 1000. This is equal to 4 into 250. That is same as 172 into 500. So I have multiplied 2 by 250 on both sides. So that is 20 into minus 17 into 250. So this will give me minus 4250. So this is the initial x naught and y naught solution for the linear Diophantine equation. So we got 1000 equal to 172 into 500 plus 20 into minus 4250. So as a solution of the linear Diophantine equation, this will act as x naught and this will act as the y naught. Now this is the first solution. Let's find out all the other solution. So x naught and y naught are the particular solution. To find all the other solution, we have done that x naught is same as x naught plus b by d times t, and we have also done that y naught is same as y naught minus a by d times t. So just substitute this value. X naught is 500 plus b, that is 20, by the GCD, that is 4 multiplied by t. This y naught, this is minus 4250 minus the value for a, that is 172, divided by GCD 4 multiplied by t. So this will give me an expression 500 plus 5 times t, and this will give me minus 4250 minus 43 times t, and t belongs to integer. So this is the solution for the first case where we want to find the integral solution. So for this x dash and y naught belonging to z, we know that 172 times x plus 20 times y equal to 1000. This admits a solution. So that explains our first case. And now we also want to look the solution for x and y which belong to the positive integers. So letting this as the solution for the first case. And for the second case, we simply need to substitute x dash should be strictly positive and y dash should be strictly positive so that they both belong to positive integers. So this is what we need. We have already found the expression for x dash and y dash. So let us keep this as 500 plus 5t should be strictly greater than 0, and minus 4250 minus 43t should be greater than 0. So from here we can find out the range for this t. So this t is greater than equal to minus 100, and this gives us 4250 plus 43 times t. This is less than 0. So from here we can get this value t as less than minus 4250 by 43, which this value becomes minus 98.8 something. So we said that t is greater than minus 100 and t is less than minus 98.9. So we get the range as minus 100. This is t lies between this. So now you can see that because t is an integral value, t belongs to integer. So the only possibility for t is that it takes minus 99, because you notice that equality is not included here. So for this value t is equal to minus 99, we substitute back into the relation that we have already obtained here, this expression. And from there you can get the value for x dash and y dash. So what we can get here as x dash, this value is 500 plus 5 times minus 99, and we get this y dash as minus 4250 minus 43 into minus 99. So when we solve this one, we get this value as 5 and this value as 7. So for this x dash which is 5 and this y dash which is equal to 7, they both are greater than 0, and of course they belong to positive integers. So that is the second solution that has been asked in the problem. So from here we can find out the range for this t. So this t is greater than equal to minus 100, and as a corollary to our given theorem, we can simply say that whenever GCD of a and b is equal to 1, and we know that x naught and y naught is a particular solution of our linear Diophantine equation, then all the other solutions are given by this. So now this is very obvious. You can see that in our previous case we have considered that x naught plus b by d times t, this is the general solution, and y is equal to y naught minus a by d times t is the general solution, where d is the GCD of a comma b. So whenever this GCD is equal to 1 as given in the statement, or we can say whenever a and b are relatively prime, and obviously whenever they are relatively prime, so this 1 will always divide c. So whenever a and b are relatively prime, there is a guarantee that the linear Diophantine equation have a solution. Now let us consider some more example on Diophantine equation, and we'll see whether these can be solved or not. So the first example is 6x plus 51y is equal to 22. Now we want to see whether this Diophantine equation is solvable or not. So this is the only question. Diophantine equation is solvable or not, and if it is solvable, how to find the solution we have already seen in my previous example. Here GCD of 6 and 51 should divide 22. That is the condition. Now what is the GCD of 6 and 51? We know that 3 divides 6 and 3 also divide 51. So GCD of 6 and 51 is 3 and 3 divide 22. Is it true? No, this does not divide. So this means the given linear Diophantine equation, this is not solvable. So we do not directly start writing the solution unless until we have not checked the condition. We must always need to check whether the solution is existing for a linear Diophantine equation or not. Let's take one more example. This is 33x plus 14y equal to 115, and we want to check whether GCD of 33 and 14 divides 115 or not. Let's see what is the prime factorization for 14. This is 2 into 7. For 33, this is 3 into 11. So we can see there is nothing common. So obviously the GCD of these two numbers is 1. They are relatively prime, and 1 divides 115. So this is true. So this means the current linear Diophantine equation, this is solvable.